Good day, grade 12s. Welcome to the second lesson on work, energy, and power. In the last lesson, we learned about work, and in this lesson, we're going to learn about energy and how it relates to the concept of work. So energy is defined as the capacity to do work. In other words, the ability to do work. In other words, the energy of an object or system can be calculated by calculating the amount of work that it can do. So if we know how much work something can do, then we know how much energy it had. The unit of energy is the joule, and it is a scalar quantity. So remember about work, I could actually just replace this. Instead of the word energy, I could have said the unit of work is the joule, and it is also a scalar quantity. So energy is the ability to do work, and therefore the unit is joules, and it is a scalar quantity. So since work and energy are related, where energy is the ability to do work, there is a theorem, and the theorem states the net or total work done on an object is equal to the change in the object's kinetic energy. Is equal to the change in the object's kinetic energy. In grade 12s, you need to know this definition. Now, there's another way we can say this. We could also say the work done on an object by a resultant force is equal to the change in the object's kinetic energy. Okay, so we either say the net work done, net or total, you don't use both words, done on an object is equal to the change in the object's kinetic energy, or we can say the work done on an object by resultant force is equal to the change in the object's kinetic energy. But what does this mean? If we put this into terms of calculations, what do we say? We're saying the net work done on an object is equal to the change in the object's kinetic energy, right? So if we wrote this, we'd write W net is equal to delta K, where delta K, you might also have seen it as delta EK, either one, is equal to the final kinetic energy minus the initial kinetic energy, okay, the initial kinetic energy, which is the change in the kinetic energy. So you can either use EK or you can use K, same thing. But the work done on an object by resultant force. So in other words, what is this? This is F net delta X cos theta is equal to delta K. So what are we doing? Relating what we learned in the last lesson, the net work done, to the change in the kinetic energy. So the net work done on an object by resultant net force is equal to the change in the object's kinetic energy. Now we're going to use, and guys, this is a very important equation at the moment. It's on your formula sheets. And it's very important because at the moment it's kind of the flavor of the month. They like asking questions about the work-energy theorem. It is a very important theorem, and you're going to use it a lot. So please make sure you understand it, and we're going to do an example on the next couple of slides. A girl skis down a 20-meter long slope which makes an angle of 30 degrees with the horizontal. The total mass of the skier and the skis is 60 kgs, and there is a constant frictional force opposing the skier's motion. And the speed of the skier at the top of the slope is 3 meters per second. Before we even read the question, let's draw a little drawing to help us understand what's going on. Now, usually they give you a drawing, and what I'd suggest you do is fill the numbers in on the drawing, or make sure that if they have already filled them in for you that you can see them. So we have a little girl, okay, and there's her hair flowing in the wind, and she is skiing. So there's her poles and her skis. Looks more like a sleigh, but never mind. And she is skiing down a slope which is 20 meters long. It is making an angle of 30 degrees with the horizontal. The total mass of the skier nut is 60 kgs. And there's a force of friction opposite of 15 newtons. And at the top, your VI is 3 meters per second. So that seems a little bit busy at the moment. So what we're going to do is do what they always ask us to do anyway, and that's either a free body diagram or force diagram. And I'm going to draw a little free body diagram. So here is my slope. And here is my dot, which represents the little girl. Now remember grade 12s, you have a pencil and a ruler and eraser. So this needs to be a nice, neat drawing with straight lines at the right angle. So I apologize if mine aren't perfect. So this is the force of gravity, and it always goes towards the center of the earth, which is why it's straight down. The only other forces acting on it are the normal force, Fn, and the force of friction up the slope. Okay, so these are the three forces, and here's a little tip. Normally, and I say normally, when they ask you to draw the free body diagram, look at the mark allocation. If the mark allocation is 3, then generally it means that you are looking at 3 forces 90% of the time. Sometimes they can be mean and nasty, but just it's a good guideline. Okay, now it says calculate the magnitude of the net force parallel to the slope experienced by the skier. Okay, so at the moment, the only force that we know parallel to the slope is the force of friction. But the other force that's acting on it, that is actually making it move, is this force of gravity. Because this force of gravity can be broken up into 2 components, the vertical component and the horizontal component. And as you guys know, this horizontal component is what's pulling the little girl down. Okay, so understand that the green and these red ones over here that I've just drawn, these 2 here, you do not fill them in on your free body diagram. Okay, only the black ones you filled in. Right, so this here, this down parallel is FG parallel. And that is the force that is pulling the little girl down the slope. And the force of friction up, this one up, is what is slowing her down and is resisting her motion down. And it says calculate the magnitude of the net force. So what do we know? We know that the definition of net force, F net, is equal to, what do we know? It's equal to the sum of all the forces. And remember they said the forces parallel to the slope. So that is going to be Fg parallel plus the force of friction. Now, we know that this little girl is moving, the girl is moving down the slope. So we're going to choose that as positive, which means the force of friction is negative. So therefore this becomes Fg parallel plus minus the force of friction. Okay. Now the force of friction is easy. They told us it's 50 newtons. So let's think about this force of gravity parallel. And we're looking at, I'm going to choose another color. We'll use the screen again. We are looking at this triangle here. And let me draw it a little bit bigger on this side. There's the force of gravity. It's supposed to be straight down. My apologies. This here is Fg perpendicular because it's perpendicular to the surface. And this here is Fg parallel. And we want this Fg parallel because that's the force that's pulling her down the slope. So we need to work out these angles. These are obviously 90 degrees because these are the vertical and horizontal components of the force of gravity. So now, as you guys should know from having done blocks on hills in grade 10 and 11, if this angle is 30 degrees, it means that this angle up here is 30 degrees. Okay, whatever the slope is, that's the angle up there, which means that this is 30 degrees there. Now, in order to get this force of gravity parallel, we obviously need to use SOHCAHTOA. Again, SOHCAHTOA. Okay. I know some of you like to use the sine rule. I tend not to use the sine rule unless I have to. So I always, if I've got right angle triangles, use SOHCAHTOA. You can use whatever you use as long as you're getting the right thing. Okay. So Fg is the hypotenuse of this triangle because that's the 90 degrees. So we've got the hypotenuse. This Fg parallel is opposite the angle of 30 degrees. So it's opposite. So we're going to use sine. So therefore, Fg parallel is equal to Fg sine theta. Plus times or minus is a minus, and the force of friction in this case is 50 newtons. Okay. So what is Fg? Fg is the mass times gravity. The mass of the skier in the skis is 60 kgs. The acceleration due to gravity is 9,8. Sine of 30 degrees minus 50 newtons. Okay, so now we put in our calculator and we go 60 times 9.8 times sine of 30, which is going to give us 294 minus 50, which is going to give us 244 newtons. And they've just asked for the magnitude, so we don't have to give direction. So the net force parallel to the slope is 244 newtons. Okay, if they just asked for the net force parallel, we would have gone 244 newtons down the slope. But all they've asked for is the magnitude, so it's 244 newtons.